All right, so good evening and welcome back to the weekly live sessions on wheel mobile robots. So we have actually entered week 7 of the course. So this being the penultimate week, we have actually covered a plenty of topics, up to the point that we have reached so far. So just to give a brief overview of what all topics that we have covered so far, in week 1, we basically covered a brief overview about various robotic systems, and we have also narrowed. Uh, we have actually seen various classifications of robotic mechanisms. We have seen the case of robotic manipulators and mobile robots, and then in mobile robots, we have actually seen various applications, various uh, methods to which, one can implement the locomotion capabilities. You can have mobile robots, aerial mobile robots, underwater mobile robots, land-based mobile robots, and then within land-based mobile robots, we had even more for several classifications, such as tracked robots, wheeled mobile robots, legged robots, so on and so forth. And then finally, since our interest for this course is wheel mobile robots, we have actually, focused on wheel mobile robots. And on week 1, just to finish it off, we have actually defined the notion of degree of mobility, degree of maneuverability, degree of steerability. These are very relevant degrees, that we would be often referring from the context of a mobile robot or a wheel mobile robot. And then on week 2, we have actually we were discussing the kinematic modeling of various configurations of wheel mobile robots. Like we have seen, how to develop a kinematic model for any general wheel mobile robot configuration, right? Such as the one that moves like a tricycle, the one with 4 mecanum wheels. We have seen the classification of uh, wheel mobile robots based on whether or not they are holonomic or not. And then moving on from week 2, on in week 3, we have actually derived the dynamic equations of motion, which are essentially the governing equations of motion of a wheel mobile robot. And then on week 4, we have actually discussed uh, the uh, the ways with which, or the sensors that a mobile robot would use for sensing and perception, sensing the environment around it and extract useful information from whatever it has been sensed. And then on week 5, we were discussing more on localization, how a robot would, localize itself on a map, which is to be supplied into a robot. We have seen, the localization based on, probabilistic methods, based on uncertainties, so on and so forth. And on week 6, we have actually we have actually discussed several navigation algorithms, algorithms for navigation. And then moving on to week 7, now that we have covered all the relevant topics, this week we would be discussing topics regarding motion control, right? Design of various motion controls, how they are classified, classification of various motion controls, and how to design a motion control. What are the parameters, parameters that are important in designing a motion control. So we will be discussing those topics, for this session, and we will be solving some problems in the later half of this session. And to top it off, on week 8, we'll have a general overview of various control hierarchies, that we would be implementing on mobile robots. All right, so moving on to the main content of this topic this week, which is motion control. So as before, we would just, for the first part of the lecture or first part of the session, we would have a very brief overview, or a very brief summary of the topics or key points that was delivered through the lectures. So moving on to a basic introduction to motion control, let's see what defines a motion control. So motion control, or a controller, is a subfield of automation encompassing the systems or subsystems involved in moving parts of machine in a controlled manner. So, like as you would know, a robot comprises of various subsystems, right? Like in the context of a robotic arm, it has the rigid serial connection of rigid bodies, and then it has actuators, it has sensors. So when coming to a mobile robot, although it may not really have as many rigid bodies as a robotic manipulators, it still has various subsystems, right? It has its own robot chassis, it has its actuators on the wheels, it has its own sensors, and again, the subsystem does not mean a singular robot, right? It could mean it could actually mean a multiple number of robots working in a coordinated sense. Like multiple robots could collaborate to achieve a achieve a common goal. So each of these robots could be considered as subsystems, right? So what a controller does is that it basically coordinates all of these subsystems so that in a controlled manner, so that a common goal can be realized. Then motion control is often closed loop. So it monitors the actual path and corrects for position or velocity errors. So as whatever we have covered until week 7, it basically gives you the tools to plan a path from wherever the robot is currently. Maybe I'll call this position as start position and our target goal positions. So whatever we have discussed until week 7, we until week 6, actually we were discussing algorithms to implement, a trajectory or to implement a path from a start position to the goal position. So once you have established or once you have developed a path like so, like so, the purpose of a motion controller is to ensure that the robot follows this set trajectory, right? Because in real life, there is a high chance that the robot may wander away from this desired trajectory, right? Because of some external disturbances, maybe due to unmodeled dynamics, things that we haven't considered in the modeling of modeling of the governing equations, or maybe due to external disturbances, probably wear and tear. There are lots of things that could destabilize or forces a robot to wander away from the predicted trajectory. So what a motion controller is that, like, if the error grows beyond the limit, or if error goes beyond the threshold, the motion controller will try to bring the robot back to the desired trajectory. That's what the purpose of a motion controller is, right? Like if the robot has to, if the robot is currently here, you know maybe due to some unmodeled disturbances, if the robot starts from the start position and it diverges into some other position, the motion controller will try to bring it back to the into the desired position, and finally, it'll have to uh, dock into that goal position, right? So that's the main purpose of a motion control. And in point 3, a motion controller contains the motion profile and target positions for the application, and creates the trajectories for the motor and or actuators. So you see all the path that we have already defined, using whatever we have learned up to week 6, will be fed into the motion controller, and the motion controller would actually give the commands, or would give input commands to the actuators or motors so that the robot can realize that set trajectory. So typically, the control is basically a feedback process. So a typical control loop of any robotic system would look something like this, right? So we begin with our robotic system. So it'll have its own outputs, whatever the robot executes. Maybe you can call this as x dot and x double dot, which are its trajectory. You can actually measure the trajectory using some sensors. So this will pass through some sensors, right? And the actual position. So I'll label these as the actual trajectory. And we would be feeding a desired trajectory into the controller. So if I call this as desired trajectory, whatever we are giving as inputs, maybe I'll label them as xd, xd dot, xd double dot. And if there is any difference between the desired trajectory and the actual trajectory, the controller, which would be somewhere around this point, would give the appropriate control signals into the robotic system, right? So this is basically a loop, an ongoing loop. So whatever the robotic system currently executes, that will end up as its actual trajectory, which can be measured through some sensors. And if there is any deviation between the sensor reading, which are the actual trajectory coordinates and the desired trajectory coordinates, the controller would give the appropriate inputs into the motors of the robotic system. So yeah, that's how a typical control loop of a robotic system would look like, and we would be actually discussing how to design several certain control laws in order to achieve uh, performance characteristics. All right. So yeah, that's a brief overview of motion control and why we need motion controllers. So why do we need motion controllers? So the first point says for robots, it's impossible or very difficult to obtain an exact dynamic model of the robot due to many unavoidable reasons. So like just we have actually covered this point. Because we have seen in on week 3, how to define the governing equations of motion, which can be written in a compact form as tau would be d of zeta dot plus n of zeta, right? This is the governing equations of motion of a wheel mobile robot, where this tau is the input that we would be giving to the actuators. D would be the mass matrix. Zeta dot is basically the acceleration vector, in terms of the coordinates that you are, writing these equations of motion. And n of zeta is a vector of Coriolis and centrifugal effects. So, you know, only a very limited things can be modeled using these equations of motion, right? There are several other things, that is not taken care of by these equations of motion, probably, due to effects, effects due to, joint clearances are not taken care into this. And then effects due to friction, are not even taken care of into this equation or by this equation. Then there could be some inherent flexibility within the robot, because the material is not 100% rigid. Material will have its own flexibility. So effects due to that is also not taken care of by this equation. So that, like, if you try to exert a force, if you try to exert a force on the ground, some of that forces would be dissipated within the robot itself, because of that flexibility or the compliance within the robot itself. So a lot of things are not cannot be taken care of by these equations of motion, and as a result, it will not the actual robot will not move uh, as per the prediction by this model. So, like, in order for you to correct the actual motion into the desired motion, you would need some controller, which would correct the actual path into the desired path. And another thing is presence of external disturbances and parameter variations, which are inevitable in robots. So external disturbance could mean, probably an unanticipated force that is acting on the mobile robot, or maybe, anything that is not anticipated by the controller. You could probably call them as external disturbances. And another thing is called parameter variations, where the constant parameters, we consider a lot of parameters as constants, but in reality that may not be the case. Like, for example, if a mobile robot is actually operating on a fuel, right? Maybe an aeroplane or an aircraft or a autonomous vehicle, working on maybe some sort of fuel. The weight of the fuel is basically a depletable resource. So as time goes by, the weight of that system, changes. And there are lots of such other parameters, that could change over time. So, due to, uncertainties in estimating that parameter in real time, you know, uh, the robot may not actually follow. The actual robot may not follow, is being, what that is being predicted by these equations of motion. So those are the reasons why we need a motion controller. So regarding design of motion controllers, there were certain philosophies, that was followed throughout the decades. So let's see some philosophies, just to have a brief summary of what can be used. So in the mid 70s, we call them this scheme as classical robotics. So in this scheme, the governing equations determine how the robot would move, right? So we have this exact dynamic models, the one that we have actually you know, derived in week 3, which is which is something like tau would be d of theta dot plus n of theta. Right? So we expect that this model pretty much covers everything. This would pretty much model an actual robot in a very how do you say that, in a very accurate manner. So whatever we have modeled in week 3 using the governing equations of motion, we consider our robotic system uh, to closely match our actual robot, to closely match what is being modeled using this governing equations of motion. So assuming going by that assumption, we don't really need any sensors, because we consider that this is how a robot is going to move, right? Because we consider everything to be modeled by these equations of motion, but in fact that is not true, as we have seen earlier. And then because of that fact, we don't need any sensor. So the robot will move as per how these equations of motion, as per these equations of motion. So like once you input the trajectory, so the coordinate theta dot would represent the trajectory. So once you plug in the trajectory into this equation, you would get the torque vector tau as outputs. That is what you would be feeding into the motors, and then the robot would execute its motion depending on this governing equation. So that's how it used to be done earlier in mid 70s. And the approach completely shifted in mid 80s. And now we use something called a reactive paradigm, where we completely disregard the model. We don't we actually completely disregard the model, and then we relied completely on sensing, right? So one example is we can actually sense the difference between the actual coordinates. So I'll write the actual coordinates as theta actual, and then we would input. We would always have an estimate. We would always have an idea of what our desired trajectory should look like. So I'll write the desired trajectory coordinates as theta desired, right? And the actual trajectory coordinates are obtained by the sensors. Whatever the robot is currently executing in real time, it can be obtained from the sensors. And theta desired is actually what we give into the controller. So the difference between the actual trajectory and the maybe the desired trajectory, this we would be giving an input to the robot based on this difference, right? So this is how that PID control came into existence, because we would basically give a control input in this form, maybe the control input tau as kp multiplied by uh, the difference in the position error plus kd multiplied by the derivative of the position error, plus maybe you can also have an integral term, maybe ki multiplied by the integral of the error between the actual and the desired coordinates. So each of these terms will have varying uh, uh, varying influence on the on how a robot would react for this control input, right? Basically, this KP term would have a measure of how the control input would be proportional to the error, uh, and that proportionality constant would be determined by this KP value. And KD is basically would contribute the rate at which the error is actually increasing or decreasing. So that this term would actually contribute to a control input depending on how fast, or the rate of change of the error. And this integral term would basically give you a cumulative would give an input based on the would give uh, a component that is actually a representative of the error that has accumulated over a period of time, right? For example, if you have a steady state error, maybe if this is the decide state, maybe I'll call this as sigma decide. And over a period of time, if the actual trajectory is something like actual, there is probably going to be a steady state error, because the actual error may not you know, fully be eliminated, because there is going to be some steady state error, because most of the controllers are basically asymptotically stable. That doesn't necessarily ensure the elimination of this error. But if you have this integral term, this steady state error could also be could be taken into account, because all the steady state error would be accumulated, and an appropriate control input, corresponding to this accumulated steady state error would be supplied onto the motors. So that's how this reactive paradigm would do, or the philosophy behind this reactive paradigm, which is mostly which would give a control input based on the difference between the actual and the desired trajectories. And then on since 1990s, we had a hybrid scheme, which would which would have a model based control at higher levels, and uh, probably a sensor-based or a reactive scheme at lower levels. So, like for example, if you have, if you have a multi-link robotic arm, for this arm to execute a specific trajectory at this end effector coordinates, you would want to know what should be the how much these joint variables should be moving, right? To achieve this and final end effector position, you should be able to determine, how much degrees or how much or what should be the trajectory of each of these joint variables. So we do that using the model information, purely using that inverse dynamics model. So that uh, for a given trajectory for this end effector, what should be the trajectory for each of these joints? And once you have that information, you would use the pure sensor feedback so that you would be able to estimate the inputs or the control inputs, the torque necessary for the actuators. That is done using the uh, uh, in that is done using that reactive paradigm at lower levels. So maybe you can consider the higher levels to be the manipulator level and the lower levels to be at the actuator levels. And then we have actually seen in this very courses about probabilistic robotics, which which is which employs a seamless integration of models and sensing. So this would basically takes care of the inaccurate models and limited sensing. So our mathematical models are always going to be inaccurate because there are a lot of physics that uh, we cannot account for, right? For example, maybe the joint clearances, the dynamics due to wear and tear. All these things cannot be taken care of by the dynamic model. So probabilistic model acknowledges the fact that there is always going to be some inaccuracies or uncertainties in the robotic model. And our sensor, whatever information that we obtain from the sensors are also pretty much limited because, whatever information we gather from the sensors, it will be riddled by noise, and the readings could also be influenced depending on the sensor characteristics. We have actually seen plenty of sensor characteristics on week 4, and how good a sensor samples, would completely depend on the sensor specifications or the sensor's characteristics. So probabilistic models basically integrates whatever information we can gather from the model. So whatever information we acquire from the model will always have some uncertainties associated with it, right? And the uncertainties can be brought down using, by fusing the information that we acquire from the models, uh, using the information from the sensors, right? So we have actually seen, the error propagation models in week 4. That in essence, that is what we basically do. We fuse our information from odometry, which is uh, 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 purely from the interior of the robot. And then we would fuse that information from odometry with the information from the sensors. Yeah, so that's about probabilistic robotics. And then later on, probably very recently, since 2015, we use data-driven models. So until now, to define the kinematics, we would have to write down the kinematic equations of motion to define the kinematics. And for dynamics, we have to derive the Euler-Lagrange. We have to derive the equations of motion using Euler-Lagrange method or Newton-Euler method. But recently, for deriving kinematics, we don't really have to rely on deriving the models. We could essentially teach a robot using multiple instances, right? Like for example, if you consider, if you have a 2 degrees of freedom robotic arm like this, we can actually teach the robot that if the robot is in this configuration defined by this x and y coordinates, probably I'll define this by x1 and y1. The join variables would be theta 21 and theta 11. Where this top number or so superscript basically depicts the instance, right? And with this approach, we can actually teach the robot for multiple such cases. So maybe if this is xy, for the second instance, theta 2 1, sorry, theta 2 2 and theta 1 2 for the second instance, can be recorded. So we repeat these experiments for multiple such instances, for any given x and y, what should be the theta 2 and theta 1. And then we, try to create a map, or we try to create maybe a regression model, or probably plug this into a neural network so that, for any such inputs, any input x and y, the model would give you the corresponding outputs in terms of theta 2 and theta 1. Right? So whatever we used to determine from kinematics, a neural network would actually learn the internal physics, by using multiple instances, and it would do the same thing. It would give you back the same thing. Whatever a kinematic model is. So yeah, those are the main uh, control approaches that has been uh, put to use throughout the decades. And then let's see some procedures and objectives of motion controls. So going on to procedures, the control design can be divided roughly into the following steps. So the first step is basically familiarization with the physical system under consideration. So like depending on the physical system you are considering, you have to familiarize yourself with its physics, which is completely defined by its kinematic equations as well as the equations of motion, the dynamic equations of motion. And once you have actually once you have accustomed to that physical system, you model it mathematically. You model your system mathematically, and once you have a mathematical representation of you know once you have a mathematical representation of your robotic system, you then specify your control specifications, right? Maybe how fast your controller should converge to the desired location. How many overshoots can it have, over the desired trajectory. All these things can be specified, has to be specified under the control specifications. How fast it should converge. Is it allowed to have any sort of oscillations? All these things comes under control specifications. And moving on to objectives, control objectives, the main objective of a controller is to have to be stable, right? So if the control input is actually if the stability of the control input is not ensured, you know it can probably, the control input can actually be very huge, very large if it goes out of bounds, and it can potentially damage the robot. It will give some very huge, very large control input, and probably it can lead to some disastrous consequences. Then another thing is regulation, right? If you have a robotic, if you have a start point, where a robot is currently at, and if you have a goal position, the controller should ensure that the robot would actually move from the start position, and it would realize its goal position. And trajectory tracking is also tells you the same thing. But in fact, in a trajectory planning, the path or the trajectory from the start position to the goal position, right? Where the trajectory is defined by the position, the velocities, and accelerations at each and every point within this path. So in trajectory tracking, the position, velocity, and acceleration within of each of these points within this path will have to be followed, right? So it is not enough that the robot reaches the goal position somehow. The velocities, the accelerations will also have to be followed at each and every instance of this path. And then finally, we will also have to deal with optimizing the control parameters, right? Maybe the gains, the control gains. We would see this eventually in subsequent slides. We need to make sure that the control gains are all optimized so that this would meet our control specifications. Uh, so now we move on to a broad classification of motion controllers. So, it can be classified in two ways. The first one is called motion-based or model-free control schemes, where it does not rely on the mathematical models. It purely relies on the sensor data, right, or the feedback. So, if you have a desired trajectory, but the robot executes an actual trajectory, its own trajectory. Uh, then whatever the robot executes can be measured using sensors. And a control input that is proportional to the error between the actual and the desired trajectory would be fed uh, into the robot. So we have seen this earlier. We called it the reactive scheme. So in a model-based scheme, we rely on pure feedback, pure sensor-based feedback, and this is pretty much easy to use, right? Like since we are not developing any mathematical models, this can be universally, accommodated, irrespective of the type of robotic system that you are working on. The principle can be adopted pretty much anywhere. And as a result, you can actually see that you can actually call it to be easy to use because it's pretty much universally adopted, irrespective of the kind of robotic system that you're working with. But it's a bit sluggish, and it produces poor tracking performances, right? Because you don't really have any insights about about the model, right? Like for example, if you consider a mobile robot like this, right? And you know, uh, from the physics, due to some physical characteristics, the robot, he is a bit hesitant, or it has some inertia to move along the lateral direction, but it can easily move. It can actually easily move along the longitudinal direction, right? But if we actually modeled this robot, we could actually make use of the fact that, it has an inertia along the lateral direction. So, we probably require more control or more effort to move in this direction, right? Because as you know, if you model a robot, you have this inertia metrics available, right? You model this inertia metrics, and inertia metrics would have the information, regarding regarding the resistance of a robot to move in any of its direction. So if the robot actually had some inertia to move along the lateral direction, that dynamics would be captured by this inertia matrix. And as a result, if the robot has some inertia to move in this direction, but the robot has to move, the control input would be amplified. The control input would be somewhat higher if the robot has to move in this direction, right? But since we are using a model-free control scheme, we don't know whether the robot has some inertia to move in this direction. So, we have to rely on the sensor's feedback That will probably take a long time for the robot to get up to speed, right? So, but if you readily knew that the robot had some inertia, to move in that direction, we could have actually amplified the control input, or we could have given the appropriate control input. So using model free, we would completely miss out that detail. And as a result, such models are a bit sluggish, and it produces poor tracking performance. So if you consider, this to be the desired trajectory, and if the robot is ended up somewhere around here, it would probably take a long time for the robot to get back to the desired trajectory. Right. That is about model-free control schemes. And another control scheme is model-based control schemes, purely using models and no sensors. So, these are comparatively efficient and simple because, as I said, if the robot has different inertias along different directions, that physics will be captured by the models, and appropriate control inputs can be given, to compensate for that. But a drawback is that, you need to have an accurate model of the robot, right? So maybe if your robot works on a very controlled environment, without any disturbances, maybe, and if you can accurately model the physics or, the dynamics of a robot, maybe a pure model-based scheme, can probably work. So that is one classification, whether the controller is motion free or whether it is model based. And again, there are some other philosophies in robotic controls. We call the philosophies as robust and adaptive controls. Like we'll have a brief overview of what those philosophies are. So the implicit assumption in most of the existing control schemes are the model is accurately known, or the constant physical parameters are accurately known. So in designing a motion controller, we would actually assume that whatever we modeled using the governing equations of motion, that is actually a very close approximation or a very accurate approximation of the real physical robot. And the constant parameters, maybe the length parameters between each features of the robot, the weight of the mass of the robot, mass of various components, maybe the diameter of the wheels, the coefficient of friction of the wheels and the ground. We consider all these parameters to be constant, and we also assume that they are accurately known. But in real life, that may not be the case, right? The parameters, the constant parameters could be changing, and we may not have an exact estimate of such parameters. So to deal with absence of this above idealized assumptions, we have these two schemes. The first one is called robust control, which aims at controlling with a small error a class of robotic manipulators with the same controller. Right. So if the errors are within a bound, right? Like if we are certain that the errors in estimating the models, the mathematical models, and if you also consider the fact that the errors in estimating the constant physical parameters are also within a bound, we can use the same control parameters. Maybe we can use the same control gains in order to achieve a goal. So such philosophies or such control schemes are called robust control. Even if there are small errors in it, we can still use the same control parameters. It would give you a very acceptable result. But we have to ensure that the errors are within some bounds. The bound of the error will have to be known in advance. Another aspect is adaptive control, which deals with the uncertainty in system parameters. And it requires the precise knowledge of the structure of the system. So in adaptive control, we accept the fact that the parameters are not known, and there is always an uncertainty associated with these constant parameters. Maybe the coefficient of friction. Probably if the tire, when it is brand new, it would probably have a very high coefficient of friction. But as it warms down, the coefficient of friction would get decreased. Probably a lot of other constant parameters, which we assume as constant, would change over time. So in adaptive controllers, the control parameters, the control gains would keep on changing, or would adapt based on the uncertainties, or based on the whatever knowledge we have on the system. So that's how this adaptive control scheme, the philosophy behind the adaptive control scheme, uh, basically tells. And another control scheme that we have considered in the lectures of week 7 is kinematic control, where we only use the kinematic models for designing motion control of robots. And then we also see dynamic control, where we use the robot dynamic model, or the actual governing equations of motion, to design the motion controller. And another important control scheme that we have actually seen is the cascade control, which uses a kinematic control in the outer loop, and basically uses a dynamic control in the inner loop. But if you can recall from the lecture, we require our robotic system to be expressed in a particular form. We call them as an input affine form, right? So this controller can only be implemented when we can represent a robot in a specific form. So we would just briefly go over some of these control philosophies. We would see this kinematic control scheme, and we would see a couple of examples from the dynamic control scheme. So in a kinematic control scheme, we have two desired parameters. We have a desired position of a robot as a function of time, and we also have a desired velocities of the robot as a function of time. So, like for example, if we have a start position like this, and we have a goal position like so, so the path from the start position and the goal position, it can probably be discretized into probably n number of discrete coordinates, and the position and velocities of uh, each of these points, maybe eta d of t and eta d dot of t, will be, these are basically our desired trajectory coordinates, right? And from the mathematical models, we have the actual positions, right? So these actual positions are available from the sensors. You can use the sensors to estimate or to determine the actual positions. And we also have this Jacobian matrix. We using the mathematical models that we have considered, in the earlier weeks, probably in week 1 or week 2, we can actually derive, the Jacobian matrix of a mobile robot. So these are the available information that we have, right? And in the kinematic control scheme, we need to find the velocity input, that we should be giving, that we should be supplying into the wheels. So, like for example, if you have a differential mobile robot like so with two wheels, so for this robot to follow maybe a desired trajectory, eta d of t and eta desired double dot of t, we need to find the control inputs omega 1 and omega 2. Maybe I'll call these as control inputs. Right? And so we do that using, we do that using uh, the kinematic equations. So we have to find this zeta vector. But from the kinematic model, from the kinematics of wheel mobile robots, from kinematics, we know the relation between zeta and eta dot. So eta dot is j of eta multiplied by theta, where theta was the velocity coordinates of the body fixed frame of reference, which were denoted as UVR, and eta dot is x dot, y dot, and psi dot, which are the velocity coordinates in the inertial frame of reference. So for any given eta desired dot, you have to find out, this theta, which is the control input. Right? So once you estimate theta, you know one more relation. Theta is nothing but W multiplied by omega vector, where this omega vector is omega 1, omega 2 for a differential wheel robot. So once you have this desired velocities, you can find the theta by pre-multiplying this Jacobian matrix with this left-hand side. And once you have estimated the theta, you can estimate this omega vector by multiplying this, pre-multiplying this W vector with the left-hand side. So if you do that, you will get this omega 1, omega 2 vector, which are nothing but the control inputs. So that is how you find out the kinematic control inputs of a wheel mobile robot. So you can do this in two ways. You can probably use using feed forward control, just like an open loop control, where theta is nothing but if eta desired dot is j of eta multiplied by theta, you can determine the theta as j of eta inverse eta desired dot, right? And once you obtain this, then you can obtain omega 1, omega 2 as W inverse theta, where this W you can derive on your own from using the mathematical models we have considered in week 2. So this is basically an open loop controller. There is no closed loop. There is no input from the sensors, and you can simply use the kinematic equations just for estimating this control inputs. But there is always an issue if you are using this open loop control law. Like for example, if I consider this as the decide start position, maybe I'll write this as decide start position, and if you have a decide end position. So this eta vector would define a trajectory from the start position to the end position. I'll call this as eta decide dot as a function of time. Right? So this is how the trajectory would look like, maybe an upward curve. But if your actual position is not coinciding with the decide start position, so if this is your actual start position, right? So as you can see, the decide start position and the actual start position are not coinciding. So if they are not coinciding, if you are using this open loop control law, your robot would still execute the same kind of motion, like this, an upward curving sort of motion, but the actual end position would would probably end up somewhere from the desired end position, right? Because since there is no feedback term, this error cannot be corrected later, and there is always going to be some offset between the desired trajectory and the actual trajectory. So when the robot executes its trajectory, it always ends up somewhere away from the desired end position. So to prevent this from happening, you always have to ensure that the desired start position and the actual start position always coincide, right? So you can express that mathematically using this equation, right? Eta desired of t at t equal to 0. The velocities at initial time, the desired velocity at the initial time and the actual time should coincide. Otherwise, the robot would execute the same kind of motion as the desired trajectory, but it'll end up somewhere away from the desired position. Right? So this is how the control law would look like. And this will only work when the actual the desired velocity at initial time and the actual velocity at the initial time is coinciding. Right? So this is just an open loop control and there is no feedback involved. So this scheme will not work if eta desired te at time t equal to 0 is not equal to eta dot of t or eta desired dot t equal to 0. Right? So if eta desired dot is 0, like if there are no velocities, then zeta is always going to be 0. So there is no control input. So like for set point controls, where the velocity of each point is not specified, this control law will not work because zeta is always going to be 0. So like there are specific cases where this controller, can pull off, a motion planning, but it's very limited due to this sort of, very limited due to these sort of these constraints. So this is what a kinematic open loop control is all about. Now we'll actually see a kinematic closed loop control. So in a kinematic closed loop control, we want the system to behave as per the first order differential equation, right? We actually want our robotic system to behave as per how this differential equation would behave, right? If you try to plot this equation, probably like so, maybe I'll call this x coordinate as eta tilde. Sorry, I'll call this x coordinate as t time. Eta tilde would be in the y-axis. So as this time tends to infinity, eta tilde would begin from a non-zero value, but as time tends to infinity, eta tilde would asymptotically converge to 0. Right? Where this eta tilde is nothing but the difference between the desired and the actual coordinates. Right? I'll label this as desired position, and eta is actual position. So this defines eta tilde. And we want our robot to follow this equation or this first order differential equation so that as time tend to infinity, eta tilde tend to 0. Right? So differentiating this equation, if you differentiate this equation, you will get it as eta tilde dot of t is nothing but minus lambda e raised to minus lambda t. So this equation is nothing but eta tilde t. So that becomes lambda multiplied by eta tilde of t. So the governing equation would something like this: eta tilde dot t plus lambda eta tilde t equal to 0. So our expected, dynamic of the equation would look something like this. Now, this is how we want our system to behave. And then what is this eta tilde dot? We have already seen that eta tilde is the difference between the desired and the actual coordinates, eta desired and eta. So if you take the derivative of it, you will get it as eta tilde dot as eta desired dot minus eta dot. So you substitute this into this, you will end up with this equation, right? So this is the desired velocity coordinates. And maybe this is the actual velocity. And this you can, eta tilde, you can call this as positional error. Right? So I'll rewrite that equation. Eta desired dot minus eta dot plus lambda eta tilde. Right? So I'll this should be equal to 0. So I'll take this into the other side of this equation. So we will get it as eta dot as eta desired dot plus lambda eta tilde. But from the kinematics, you know that eta dot is j of psi or j of eta multiplied by theta, right? So if I substitute this into here, you will end up with j of eta multiplied by theta is eta desired dot plus lambda eta tilde. So in this case, this should be the control input, right? This basically relates very closely with the actuators, the inputs to the motors. So from here, zeta would be j of eta inverse eta desired dot plus lambda eta tilde. So this would be the control input. This is how a closed loop control input would look like. So here, this is actually a feed forward term. There is no feedback involved in it. And this term, lambda eta tilde is actually the feedback term, because eta tilde is the difference between eta desired and eta. And eta basically comes from the sensors, which is, this is basically the actual position which comes from the sensors. Right? So you call this control input or this control scheme as the computed velocity control. Right? You call this as computed velocity control. All right. So if you input this control input into the motors, right? So at this point, you cannot directly input this the elements of this vector into the motors because you need one more stage, right? Zeta is W multiplied by omega, so omega would be W inverse theta. So you will be able to get omega from this theta. So once you have this theta, and by association, once you obtain omega, if you input that into the robotic system, the robot would behave as per this first order dynamics. So it's guaranteed that the error would converge asymptotically to 0 if this corresponds to your control input. Right. So I hope that is clear. Now we move on to dynamic control. It's very similar in derivation to the kinematic control, except that we have a few more parameters involved. So here as well, we want our robot to achieve a desired trajectory. If you have a start position, position. I'll call this as a decide start position, and you follow a particular trajectory, and you have a desired end position. So this entire trajectory can be described by eta decide of t, the position coordinates, eta decide dot of t, velocity coordinates, and eta decide double dot of t, the acceleration coordinates. So, these are the decide parameters, the trajectory coordinates. And from the mathematical models, we have the actual position. These actual positions are obtained from the sensors. We have the Jacobian models from the mathematical models. And we have the actual velocities. Again, these are from the sensors. And the inertia metrics and the vector of centrifugal and Coriolis effects. That is also available from the mathematical models. Right. So the general control equations of motion or the dynamic equations of motion of a robot would look something like this. Tau as d of zeta, zeta dot plus n of zeta. So this tau vector would be the control input to the actuators. Right. So we have to determine this tau vector so that it meets some conditions or it satisfies some conditions. Right. So our objective is to find this control input tau. Right. And our objectives are, the errors, the position errors and the velocity errors should asymptotically converge to zero. Right. If you plot the position in the position and velocities errors in the y-axis and the time in the x-axis, both the position and the velocities should asymptotically converge to zero as time tend to infinity. So those are our objectives. So how do we do that? We have, just like in the previous cases, we have two schemes. So the first one is actually the how do you call it? The first one is actually called the inverse dynamics control. Yeah, where where in this case you already know this the dynamic equations of motion, which has tau as nothing but d of zeta dot plus n of zeta. And for this in inverse dynamics control scheme, you already have your eta desired dot and eta desired double dot. Because in most of the cases, your desired trajectory would be expressed in the inertial frame of reference. These are trajectory coordinates in the inertial frame of reference. Because the reason is that we even though the control inputs are specified with respect to the robot fixed frame of reference, the reason that we are specifying the desired trajectory in inertial frame of reference is that, like, as an observer, we are also situated in the inertial frame of reference, right? But the actuators and sensors, they are actually mounted on the robot. So whatever inputs that we have to give to the actuators, it's convenient to express them in the robot frame of reference. But the trajectories and all those things, it's easier for us to visualize if they are expressed in the body fixed frame of reference. So from kinematics, we actually have eta dot as j of theta multiplied by theta. You can consider this equation to be actually, describing the actual kinematics of the robot. So in this inverse dynamic scheme, you would simply plug in, you simply plug in the desired trajectory here and find out what this theta is. Or rather, we actually need this theta dot term over here. So in order to find that, you have to take the derivative of this expression. So eta double dot would become, if you apply the product rule, it will become j of eta dot theta plus j of eta theta dot. So this would imply eta double dot minus j dot of eta theta the whole pre-multiplied by j of theta inverse. This would give you theta dot. So what you do in an open loop control scheme or an open loop inverse dynamic scheme is instead of this actual coordinates, zeta dot, zeta eta, you simply plug in, the desired variables, right? So this becomes zeta desired dot, this becomes theta desired. So this becomes zeta desired, and this becomes eta desired. Everything becomes desired. And, this theta, you can actually replace this theta with, this equation, j of eta inverse eta dot. So if you do that, this term becomes j of eta inverse eta desired dot. Every coordinate is desired with, every coordinate is actually replaced with the desired coordinates. Yeah, so once you have your control input, zeta desired dot, you actually have the zeta desired dot in terms of eta desired double dot and eta desired dot. Everything in terms of the desired trajectory coordinates. So once you estimate the zeta desired dot, you directly plug this into here. Right? You directly plug that over here, and then you will be able to get this tau vector. So that's about this inverse dynamic scheme. And as you can notice, there is no feedback term. There is no error between the actual coordinates and the desired coordinates. Everything is fed forward, through the control process. So yeah, that makes it that's about this inverse dynamics control law. It's also an open loop control scheme, and just like in the inverse kinematics open loop scheme, we want the initial positions and initial velocities of the desired and the actual coordinates to coincide. Otherwise, there is always going to be an offset between the desired and the actual path. Right, and similar to how you describe the kinematics, the inverse, the computed velocity control, you can also derive the computed torque or the feedback, the closed loop feedback control. And the final expression would look something like this. This is how you. This is basically the expression for the computed torque control, which is a closed loop scheme, because as you can see there are two tilde terms available in this control law. This is basically the difference between the desired and the predicted velocities, and this is basically the term which is the difference between the desired and the actual positions. right? So that's about it. And now maybe we can, solve some sample questions. I think in the lectures, we also discuss something called a cascaded control, which is, somewhat involved, which I don't want to discuss here at this moment, but there is an upcoming, there's an upcoming extra session coming up on Saturday, this coming Saturday. So if anyone wants to discuss more about that, you can let me know by the comments or comments of this YouTube video. I'll be uploading the recording in the YouTube, and probably you can ask that in comments, if you want to discuss more about, if you want to have a summary about cascade control. All right. So with whatever we have covered so far, we can actually see some sample problems. Should be fairly straightforward, with the material that we have covered. So the first question is, a robot is not only a mechanical architecture, but is also slaved by something that impacts its performance. So the correct answer from this regard, a robot is actually slaved by something, right? So if you can recall, we have actually seen a general control, a general you know schematic of how a motion control would work. We have a robot here, and whatever the robot actually executes, we can actually measure the coordinates, maybe eta actual, eta dot actual, and eta double dot actual. We can measure everything using the feedback from the sensors. And this can be compared. The actual coordinates can be uh, compared with this be the controller. So the actual coordinates can be compared with the desired trajectory coordinates. And this error, whatever error we have between the desired and the actual coordinates, the controller will give an appropriate input to the robot. Right. So the robot, which is a mechanical architecture, comprising of rigid links and motors and actuators, the execution of any task of this robot is actually controlled by this, or is actually determined by this controller. So in effect, you can actually say that the robot is actually slaved by this controller. So I hope we can actually agree that the correct answer that fits into this blank would be controller, right? Because the robot is essentially whatever the robot executes is purely determined by the motion controller. So option A would be the correct answer for this question. So that is indeed the answer. And moving on to question 2, seamless integration of inaccurate models and limited sensing capabilities is known as. So like earlier in the lecture, we have actually seen, various control paradigms, or, various philosophies, which were implemented over the decade regarding the design of motion controllers. And in the question, it asked, the seamless integration of models and sensing. So that is basically a defining attribute of probabilistic robots. So again, we can actually choose our correct answer to be probabilistic robots, which is fairly straightforward. And then moving on to question 3, it says the inverse differential kinematics or inverse dynamics is equal to, right? There are different classifications of controls in the options. So we have actually seen earlier, a few minutes ago, that this inverse differential kinematics is an open loop control scheme, or another word to call them is, we call them as feed forward schemes. And inverse dynamics also belong to the same class of motion controllers. Open loop scheme or a feed forward scheme, because essentially there are no feedback terms. Like one example is, eta dot is j of eta theta, and this is your control input. So to determine theta is nothing but j of eta inverse eta dot. But in a feed forward term, you replace everything with the desired coordinate. So eta becomes eta desired dot. So your control input simply becomes, j of eta desired inverse eta desired dot. So if you have this already known, or if you already have a desired coordinate, you simply plug that, or you simply pre-multiply that with the inverse of the Jacobian matrix, and you will get this control input. You can straight away feed that into the motor. So that makes our answer to be option B, which is feed forward or open loop control. So option B is indeed the correct answer for this question. And moving on to question 4. So in a set point or regulatory position control, the desired position vectors and velocity vectors are continuous. So the key point to consider is set point or regulatory position controls. So if you can recall from the lectures, from the lectures in NPTEL, you can actually see that there were two control tasks, right? We had this set point control, or we had the trajectory tracking control. So in set point control, if you consider the path from the initial configuration to the final configuration, we consider the velocity at each instance to be 0. So like our only goal is we want the the robot to stabilize at this final configuration, right? So it'll have to stabilize through each of these individual points, but we consider the velocity at each of these points, the target velocity at each of these points to be 0. But in trajectory tracking or in a servo control, if you consider the path from our start position to the goal position, each of these points will have their positions and velocities defined. So our robot will have to closely follow, or try to closely follow, the position and velocity coordinates at each and every point of this trajectory. Right. So in order for us to do that, the coordinates will have to be continuous. The position and the velocity coordinates of the trajectory will have to be continuous in case of a trajectory tracking control, not for the set point control. So that makes our choice, right? The choice was specifically asking for, the choice was specifically asking for set point control. And for set point control, we want, the defining feature of a set point control is to have the velocities at each and intermediate point to be 0, which makes it not continuous. So going back to the question, in set point control or regulatory control, the desired position vectors and velocity vectors are continuous. That is obviously false. If it were to be continuous, it would be a tracking control or a servo control. Okay, so the answer for question 4 is indeed false. And moving on to question 5. The second order error dynamics is stable as per the following condition. So which of this following condition would ensure that the second order error dynamics would be stable? Right. So like we'll look at, there are two parts of this question, the first part is basically the differential equation itself, the error dynamics equation itself. And the second part is basically, the constraint on this, the coefficients, right? So, which of these options are correct? So, what is this eta tilde coordinate? Eta tilde is nothing but the difference between the desired and the actual coordinates, right? And this is the difference between desired and actual position coordinates. And eta tilde dot is the difference between the desired velocity and the actual velocities. And eta tilde double dot is the difference between the desired and the actual accelerations, right? And this is basically a second order differential equation. Eta tilde double dot plus lambda 1 eta tilde dot plus lambda 2 eta tilde. So how do you choose lambda 1 and lambda 2 so that the system is stable, right? How do you choose lambda 1 and lambda 2 for the system to be stable? So how do you interpret stability? So stability, you can call a system to be stable as, when as time tends to zero, the errors in the position and velocities, sorry, as time tend to infinity, the errors in position and velocity asymptotically tend to zero. So like if I plot a graph where in x-axis you have time, and in the y-axis, if you try to plot the position error and the velocity error, so as time tend to infinity, the position errors and the velocity errors, both of them should asymptotically converge to zero. That is what the notion of stability essentially means. And in order to establish stability, we need to choose the correct constraints on these coefficients. And this being an second order linear ordinary differential equation, you can basically the complementary solution, right, for this homogeneous equation would look something like this. Eta tilde of t would be c1 e raised to s1t plus c2 e raised to s2t, where the c1 and c2 are some arbitrary constants, and s1 and s2 are dependent on the system parameters. S1 and S2 depends on lambda 1 and lambda 2, but C1 and C2 basically, they'll only depend on probably the boundary conditions. So if this were to be stable, if eta tilde were to converge to zero, we want this term S1 and S2 to be negative, right? Because C1 e raised to minus some constant into t, as time tend to infinity, this term would go to zero and this term would also go to zero, right? And we know for a fact that S1 and S2 are nothing but, the roots of this quadratic equation given by minus lambda 1 plus or minus root of, lambda 1 square minus 4 lambda 2 by 2. So S1 and S2 are determined by this quadratic equation. And if S1 and S2 were to be negative, this lambda 1 and lambda 2 will have to be strictly positive. Then only this term would asymptotically converge to zero as time tend to infinity. So that makes our choice for or our constraints for the control parameters lambda 1 and lambda 2 to be greater than zero, should be greater than zero. So that makes our option to be C, option C. So I hope we can agree on that. So let's checking the correct answer. Option C is indeed the correct answer. So moving on to question 6. This is a somewhat involved uh, involved in math. The question says the computed input control law of a land-based mobile robot can be given as. So, which of the following option corresponds to the computed input control law? So, this is actually a closed loop. Whenever you see a computed input, this is a closed loop control. Right. So, let's see how we can derive this closed loop control law. So, like, we have the two governing equations, starting from kinematics, right? From week 2, we know the kinematic equations to be. So I'll write it over here. Maybe from week 2, we the topics we covered were kinematics. And from kinematics, we know the governing equations, or we know the kinematic equations, eta dot to be j of psi multiplied by theta. So I label this as equation 1, right? And these are the velocity coordinates in the inertial frame of reference. Velocity coordinates in inertial frame of reference. And theta is nothing but the velocity coordinates in body fixed frame of reference. Right. And then from week 3, from dynamics, we also know the governing equations of motion, right? The governing equations of motion, which is nothing but tau as d of theta multiplied by theta dot plus n of theta, where this tau is the control input. This is the force or the torque that we would supply into the motors. And d is the inertia matrix or inertial matrix. And zeta dot is nothing but the derivative of the velocities, which is accelerations. And this n vector is nothing but the vector of centrifugal and Coriolis effects. We have actually seen the derivation of all these things in week 3. So I label this as equation 2. So our control objective is to force the system to behave as per the second order aerodynamics. So I'll write it over here. The objective is to force the system to follow the second order dynamics eta tilde double dot plus lambda 1 eta tilde dot plus lambda 2 eta tilde to be 0. So I'll label this as equation 3. So in the previous question, we have actually seen that if we force our robotic system to follow the second order aerodynamics, the positions and the velocity errors would asymptotically converge to zero. That is what we want, right? As time progresses, we want the error, the error between the desired and the actual coordinates to be as zero as possible, as close to zero as possible. So I'll substitute eta tilde double dot as the difference between the desired acceleration and the true acceleration, eta double dot. Right. So if I substitute this into equation 3, I'll get this as eta desired double dot minus eta double dot plus lambda 1 eta tilde dot plus lambda 2 eta tilde. This is 0. So I'll just rearrange this. I'll bring this eta double dot over to the other side. So I'll end up with eta double dot is nothing but eta desired double dot plus lambda 1 eta tilde dot plus lambda 2 eta tilde. So I'll mark this as equation 4. Okay. All right. So up to that, I hope this is fine. Then going back to equation 1, right? We have this eta double dot term over here, and here we have this eta dot term here. So if you differentiate this equation 1 with respect to time, we'll get an expression for eta double dot. So differentiating, I'll just write it over here. Differentiating equation 1 with respect to time, I'll get eta double dot as, I'll apply the product rule, j of psi dot multiplied by theta plus j of psi multiplied by, I think it's better to stick with the j of eta, just to be consistent with whatever we have learned in the notes. So j of eta dot theta plus j of eta theta dot. So I'll label this as equation 5. So while comparing equation 5 and 4, so on comparing 5 and 4, you will get it as j dot of eta theta, j dot of eta theta plus j of eta theta dot. This would be equal to the RHS of equation 4. It is nothing but eta desired double dot plus lambda 1 eta tilde dot plus lambda 2 eta tilde. All right. So up to that far, we have actually obtained. So what I'm going to do is I will essentially try to find out an expression for zeta dot, right? So I'll have to move this term over to the other side. So that makes it eta desired double dot, eta desired double dot plus lambda 1 eta tilde dot plus lambda 2 eta tilde multiply minus j dot of eta zeta, the whole pre-multiplied by j of eta inverse. This is nothing but zeta dot. So I'll label this as equation 6. Right, zeta dot. Then comparing equation 6 and equation 2, we also have a zeta dot over here, right? So in place of the zeta dot, I'll find an expression for zeta dot from equation 2, right? And I'll put that in place of the zeta dot. So from equation 2, this tau vector minus n of zeta, the whole pre-multiplied by d of zeta inverse. This is nothing but zeta dot. Hope I'm right. So I'll call this as equation 7. And now comparing equation 7 and equation 6, we will end up with j of eta inverse eta desi double dot plus lambda 1 eta tilde dot plus lambda 2 eta tilde minus j dot of eta zeta. This would be equal to d of zeta inverse tau minus n of zeta. All right, so from here, we have to find out this vector tau. That is your control input, right? So from this equation, you have to find the expression for this tau, which would be your control input. So again, on further rearrangement, it would be something like d of zeta, j of eta inverse, eta desired double dot plus lambda 1 eta tilde dot plus lambda 2 eta tilde minus j dot of eta. And in place of this zeta, I will, I'll replace it from this equation 1, right? Where zeta is, j of eta inverse eta dot. So I'll replace that directly. So j of eta inverse eta dot. Then plus we also have this n of zeta equation. Yes. So this would be the expression of the control input for the computed control law, So if you supply this control law into the robotic system, we are trying to force the robotic system to follow this second order error dynamics, right? So if the system follows the second order error dynamics, the asymptotic stability can be assured. Asymptotic stability of the system can be assured. Which forces, which essentially means as time tend to infinity, the errors in position and errors in velocity would asymptotically tend to 0. So this would be the expression for the computed torque control. And going to the question, which essentially asked for an expression for computed control law, I think this is what we have derived. This is exactly, what we have derived previously. So going on to question 7, Uh, what is the primary or important control objective? We have actually seen the most important control objective is to ensure the stability. Every other things comes secondary, because if the control input is not stable, the system can uh, it could probably end up disastrous. A huge spike in control input would force the system to be unstable, and it cannot be recovered. So the most important thing to be ensured for the control objective is stability. And in all the control schemes, in all the closed loop control schemes that we have discussed earlier, it ensures asymptotic stability. Asymptotic stability in position as well as velocity. Which they are inherently stable. If you go with some advanced controllers, the stability will have to be proved, or the stability will have to be ensured using some analysis. But whatever we have designed so far, it has inherent stability. All right. So that's about question 7. Moving on to question 8. Dash is the change of state at any instant in time of a body or bodies. So like if a body is in a state in time t equal to 1, and if the body changes its state at time t equals t plus 1, a mere change, in state, uh, we would call that as motion. Motion is the change of state at any instant of time of a body or bodies. This is not entirely true, because a change of state can mean anything. But if you consider from a robotics point of view, in case of a robot, a change of state often associates with motion, right? Often associates with change in position. So change of state, is akin to change of position. So a change of position, if a robot is in one position at time t and it changes to some other position, at time t equal to t plus 1, we call the change of state or change of position as motion. But we don't know how that change of position has been achieved. We simply know the start position and the end position. We don't know how it changed. It could go by this path, it could go by this path. We don't know that detail. We only know the start and end configuration. So, we call such change of states as motion. And the second statement is dash is the state of a body or bodies over a period of time. And the third statement is dash is the position of a body or bodies over a period of time without worrying about position or higher order terms. So like we'll go with the third statement. That seems to be more easier. So if we have a start position, probably like so, start position, and we have this end position. So according to the third statement, dash is the position of body or bodies over a period of time without worrying about velocity or higher order terms. So like we have all the information between the start and the end position, right? All this we have information about all these intermediate positions, but we don't know the velocities or higher order terms. We don't know the velocities at each of these points. We don't know the accelerations of each of these points. We simply know, the positions along this path. But that itself actually, depicts, it's actually the definition of path. We only know the path, but we don't know how fast the robot moves through each of these points of the path. maybe it could move very fast half of this path and then move very slowly, move very slowly as it reaches the end. Or, maybe it could start very slowly, when it is starting, and in between it can go very fast. And then as it is stopping, it would gradually, very smoothly decelerate. It could be anything, but we don't know. We simply know the path. That's all we know. So that is basically the definition of path. We know the positions, but we don't know. We have no information about velocities or higher order terms. And that leaves us with the second statement. Dash is the state of body or bodies over a period of time. So like over a period of time, we know the state. Uh, we know information about all of the state. We know the information about positions, right? We know the information of position as a function of time. We know the information of velocity as a function of time. We also know the information of acceleration as a function of time. So like we know all the information for all of these intermediate points. Collectively, we call it as a trajectory. The specification of position, velocity, and acceleration along a path is called trajectory. So yeah, in that regard, the correct answer would be motion, then trajectory, then path. I think that option is option A for the fill in the blanks. Moving on to question 9. Which of the following are open loop control laws for land-based wheel mobile robots? So like we have seen previously, we have actually seen how you can classify controllers based on whether or not they are open loop or closed loop. So like we'll just simply classify all of these following options based on whether or not they are open loop or closed loop. So inverse differential kinematics. This is this is simply an open loop control, right? Because this is the easiest control law that we have actually discussed. Because from kinematics, eta dot is nothing but j of eta multiplied by zeta, and this is the control input, right? And to if you know the desired velocities, if this is known, then finding out the control input zeta is trivial, right? It is nothing but j of eta inverse eta desired dot, right? So this is the inverse differential kinematics. Very straightforward, but it's open loop because there are no feedback terms involved in this control loop. So that makes it open loop. But computed velocity control is a closed loop. We have seen it in the session earlier, and we have also seen this in the lectures. This is closed loop. PID control is also closed loop because it has feedback terms in the control law. Inverse dynamics control is again open loop. Just like how we have seen the inverse differential kinematics, the dynamics is defined by this equation. Tau is d of zeta dot plus n of zeta, right? So you will have the desired positions, desired velocities, and desired accelerations. And if you know this, from kinematics, you can also estimate desired positions in zeta coordinates, desired velocities in zeta coordinates, and desired accelerations in zeta coordinates. So once you know all these things, you simply plug everything into these equations. You will be able to obtain the control input vector tau. So that is also pretty straightforward. And as you can see, there are no feedback terms in it. So that makes this open loop. Sorry, inverse dynamics as open loop. But computer torque control, we have seen this in one of the problems. This is closed loop. And the same goes for cascaded control. This is also closed loop. So the question asks which of the following are open loop control laws. So I think we have uh, two correct answers, which is option A and option D. Everything else is closed loop. So yeah, those are the two correct answers. Checking the answers, we have two correct options. Yeah. And then moving on to the second question. Identify the incorrect statements. So model-free control relies on pure sensing and feedback only. So model-free means, we don't have any mathematical models. We rely purely on sensor feedback. For example, this PID control law, it's a pure sensor-based control law. Like we don't rely on the mathematical models. So that statement is indeed true. Then second statement is model-based control laws are easy to use, but are sluggish and produce poor tracking performance. That is actually false. We have actually seen why this is so in at the beginning of this lecture. Model-based are not sluggish. Sensor-based are actually sluggish. One example I can tell you is that, if you have a mobile robot like this, maybe a differential wheel mobile robot like this, or it could be anything, maybe a mobile robot with four wheels, right? So let us assume that the robot can easily move along this direction. It can easily move, but maybe due to the weights or due to some inherent characteristics, the robot finds a bit difficult to move in the lateral direction. It basically finds a bit difficult to move in the lateral direction. So if you are using a model-based control, you can actually make use of this information, right? The model will capture the fact that the robot can easily move along the longitudinal direction, and it has some inertia to move in the lateral direction. You have this inertia matrix, right? So if you're using the information of the, if you're using the information from the inertia matrix, the control input would be, scaled appropriately, right? If you want the robot to move in the lateral direction, based on the information about from the model, which is the inertia matrix, the control law would give an amplified input along the lateral direction, so that the robot can move. But if you're using a model-free model-free control law, we won't be using any information from the model. So any information from the mathematical models. Instead, we purely rely on sensor feedback. So if you try to give equal inputs along lateral and longitudinal direction, the robot will actually move or react very slowly because because it is difficult, because the robot finds difficult to move in this lateral direction. So it'll react very slowly to the control input, and as a result, model free uh, control laws are a bit sluggish, and it could produce poor tracking performance. So sluggish and produce poor tracking performance is attributed to model free, not model based. So this statement is actually false. And third statement is model-based control laws are comparatively efficient and simple. Yes, they are indeed efficient. So that is indeed true for question 10. And for Fourth option is model-based control. Accurate control models of robotic system should be available. Right? In order for a model-based control law to work, not relying on any feedback, but purely on mathematical models, the accurate models of the robot system should be available. That is true, right? Because if your control input is based on a mathematical model, that mathematical model will have to closely or will have to be accurate as possible to the real physical system. So that statement is also true. So the only incorrect statement, as far as I can see, is option B. Everything else is true. Yeah, so this is basically a screenshot from the lecture videos uh, available in NPTEL. So yeah, based on these bullet points, you can easily have your own inferences, regarding which of the statements is true and which of the statements are false. So I believe option B was false, and yeah, that indeed seems to be the correct answer. The incorrect bullet point seems to be option B. And moving on to the final question, I believe. No, the second last question. In case of a holonomic mobile basis, all three states, XD, YD, and PSI-D cannot be simultaneously controlled. So for any mobile robotic system, you need three parameters to fully define its configuration, right? So you need if this is the body fixed frame of reference, XB and YB, and if this is the inertial frame of reference, XI and YI, you need two position parameters, X and Y, to locate the origin of the robot, right? And you need one rotation degree of it, right? Maybe psi-d to determine its orientation with respect to the inertial frame of reference. So in essence, you need three coordinates. And whether or not a robot is holonomic or non-holonomic depends on the fact that whether all these states can be controlled simultaneously, right? For example, in case of a differential wheel robot, right, a differential wheel robot with two driven wheels like this, this differential wheel robot can move along the lateral direction, sorry, along the longitudinal direction. It can rotate about its own axis. So like it can actually have, maybe I'll denote the frame of references like this, XD and YD. So as far as a differential robot is concerned, this configuration can move along XD. So this coordinate is satisfied. The differential robot can also independently rotate about its own axis, right? It can rotate with zero turning radius. So, this coordinate can also be achieved. So both of these can be achieved simultaneously. But what about the lateral motion? A differential robot cannot slide laterally, right? Because these conventional wheels provide infinite resistance along the lateral direction. So YD cannot be controlled. So all these coordinates cannot be controlled independently and simultaneously, right? So if this is the initial position, and if this is the final position, like this, or maybe I'll denote the final position like this, probably like this. So this is XD and this is YD. So what a non-holonomic robot is that? First, it will try to draw a line from initial position and start position. Then from its initial position, it rotates, you know, it rotates along that line of sight. Then it moves along, along the longitudinal direction. And once it reaches its final position, it'll realign, based on its rotational axis. So that's how non-holonomic robots will move. But a holonomic robot can simply slide. It can actually simply slide in one swift, smooth motion so that the final control states can be achieved. So the question says in case of a holonomic mobile robot, all three states, XD, YD, and XD, cannot be simultaneously controlled. So that is actually false. Because in a holonomic robot, all these 3 degrees of freedom can be simultaneously controlled. So like it can actually move, a holonomic robot can actually move, in the forward direction, in the lateral direction, like so. It can even move diagonally. It can rotate. All sort of motions are simultaneously possible. So the option is indeed false. Checking the answer, it is indeed false. And going to the last question of this session, robust controller deals with uncertainties in the given system parameters, and it requires precise knowledge of the structure of the system. So like we have earlier seen the definition of robust and adaptive controllers. So in case of an adaptive controller, the system parameters are considered to be uncertain. Maybe the mass, maybe the coefficient of friction, between rubbing surfaces, maybe the damping coefficient. All of these are considered to be uncertain, and they also vary with time, right? Maybe a brand new wheel have very high coefficient of friction, but as it wears down, the coefficient of friction will reduce. So in case of an adaptive controller, it will basically adaptively tune its control parameters, based on the uncertainty regarding each of these parameters, each of these constant parameters. They are not really constant anymore. They have some uncertainty regarding it. So this statement, regarding uncertainties and the controller trying to adapt its control parameters, its gains. It's actually a statement regarding adaptive control, not on robust control. So the statement is actually false from the context of a robust control, because whatever it is described here, from this point all the way to the end is actually something that regards to adaptive controller, not to robust control. So that makes this statement false. So that is indeed the answer for this question. So yeah, I have nothing else to add. We have more or less covered all sort of questions that you can expect for the weekly quiz. We have seen, all sort of problems, all kinds of problems, similar problems, which you can expect for the weekly quiz. So I have nothing more to add. So unless there are any queries, let me know. Otherwise, we can, we can end this meeting. Yeah, you can actually get the recording sessions. These are actually shared in the NPTEL website. In the course page, it is actually shared. The link to the recording sessions are shared. Yes, you can access the recordings from the course website, and I will try to upload the recording today itself because it takes some time for the recording to be uploaded in YouTube. So by tomorrow it will definitely be online. So you can check out uh, the course page for the recording links. Yeah, so I have nothing else to add. If you there are any more questions, let me know. Otherwise, we can. Okay, thank you. So I'll end the meeting for now. Yeah, thank you. Thank you for joining. Okay, so that's it. Bye.